and the stage is yours. Juan, please go ahead.
Okay, so let me start by thanking all the organizers for putting together the conference and for having me in the program. This is bargaining with evolving private information. So I'll just start by describing what I'm going to do in this paper. So in this paper, I study a bilateral bargaining game that has 3 key ingredients. The buyer is privately informed about her valuation. The seller is going to privately observe her cost of procuring the good. For simplicity, the cost is just going to take 2 values, high and low, and that cost is going to be changing over time in a stochastic way. The seller is going to make all the offers. So relative to the literature, this is a model of 2-sided private information, but there has been papers doing that. What's new is that the private information of one of the sides here, the seller, is changing over time. So there's new private information arriving over time. And let me say that, at least in this framework, it's natural to think of a seller whose cost might be changing over time because maybe her input prices are changing. Let me also say, this is well known that these models are mathematically equivalent to models of durable goods monopoly, so a seller facing a population of heterogeneous buyers. And they are, the assumption that costs are changing is also natural if you think of, the producer of a new durable good whose cost of production, might fall in the future. So, there's one question that I want to understand here is that how does this arrival of new private information here, the seller's time-varying costs, affect bargaining outcomes? So in terms of results, for most of the paper, I focus on a class of equilibria that are equilibria in which the seller's price offer each period is going to reveal her cost. And there are 3, this game is going to have many equilibria because, this is a signaling game. The seller has private information and she's making offers. So, the set of equilibrium is going to be very large. There are 3 reasons why, this is a good starting point, this revealing equilibria. First, this is kind of the natural counterpart to equilibrium in previous models in the literature, so it's going to allow me to compare to those previous models. Second, this equilibrium set is going to turn out to be quite tractable and intuitive, and this revealing equilibria are going to help rationalize certain pricing patterns in durable goods markets. So for those reasons, I focus on this class of equilibria. And my first result is going to provide a characterization of the set of revealing equilibria. There are going to be many of them, but they're all going to share similar features. So under any revealing equilibrium, trade is going to be inefficiently delayed while the seller's cost is high. And when the seller cost is low, the usual Gaussian forces are going to kick in, and trade is going to be fast at a low price. And the inefficiencies are going to be driven exclusively by the seller's information revelation constraints. And I think this is going to become very clear as I present my results. For my second set of results, I said there's many revealing equilibria. I'm going to focus on the one that's most efficient among this class, and I'm going to see what happens when the seller is able to make offers arbitrarily frequent. And I'm going to show that that frequent offer limit is characterized by a system of differential equations that describe how prices and trade probabilities evolve over time. And this is going to allow me to perform some comparative statistics that I'll describe in more detail later on. Then my last result, I'm not sure if I'm going to have a lot of time or enough time to go over it, but let me just share it with you now in case I don't. So the last result, I'm going to compare equilibrium outcomes in this model in which costs are privately observed by the seller to a model in which is the same, but the cost of the seller is publicly observed. And that model is related to a previous model that I studied in a previous paper of mine that came out in TE in 2017. What I show is that the model with public costs retains a lot of the key Gaussian elements. So equilibrium outcome when costs are public is it's always efficient in the frequent offers limit, and the seller is unable to extract any rents from high value consumers, just as in the standard cost conjecture. So relative to a setting with private costs, the surplus is larger because now the equilibrium is efficient. And it turns out that all that surplus goes to the buyers actually because the seller is unable to extract rents. And it turns out that it's going to be those buyers with higher valuations that are better off because they are able to get the good at a cheaper price and earlier. All right, so that's my short introduction. Let me, I'll spend this paper fits into a very long literature on bargaining with private information. I'm not going to describe all of it, but let me just say 2 things. First, there's some models that study bargaining with two-sided private information, but in those models, the private information of the two parties is determined at the start of the game and it's fixed throughout. My model has the private information of one of the sides changing over time. And then there's some recent papers analyzing how the arrival of public information affects bargaining outcomes. My model studies how, so in my model, I study how the arrival of private information affects bargaining outcomes. All right, let me go to the model. So, this is a bargaining game between a buyer and a seller. Time is discrete and delta is the time between two periods. At the start of the game, the buyer is going to privately learn her valuation, and the seller is going to privately learn her cost, her initial cost, which can be low or high. The low cost, I'm going to normalize it to 0. And then the seller is going to make the first offer P0, which the buyer can accept or reject. If buyer and seller haven't reached an agreement by time t, the seller is going to privately observe her cost, or her new cost. And then she's going to make a new offer PT, which the buyer can accept or reject. And if players reach an agreement by time t, the game ends. The buyer gets her value minus the price she paid, discounted, and the seller gets the price she got for the good minus the cost of producing it, also discounted. The valuation of the buyer is going to be drawn from some distribution f, which has an interval as a support. It has a strictly positive density, and the assumption that I'm going to make, which is going to play a role, is that the lowest valuation of the buyer is strictly larger than the lowest cost. So this is the gap case. So we can talk about what this assumption buys me, and it's going to become clearer as we move on. And then the seller's cost at time 0, the seller's cost can be high or low. It's going to be high with probability Q. This is independently drawn from the buyer. It's independent from the buyer's value. And then if at time t minus delta, the cost was high, the probability that the cost today is high is e to the minus lambda delta, where lambda is a positive constant. And for the paper, I'm going to assume, for the talk, sorry, I'm going to assume that the low cost is absorbing. If the cost was low yesterday, it's going to be low today with probability 1. Later, if I have time, and I do it also in the paper, I can talk about how the results generalize to the case in which the low cost is not absorbing. The main key insights are going to go through, but you'll see that having the low cost absorbing is going to greatly simplify the exposition. So I'm going to stick to that for the talk. Okay, so the history of the seller is going to record all previous cost realizations and all previous price offers. The history of the buyer records her valuation and all previous price offers. And then a pure strategy for the seller maps her histories and her current cost to a price. And a history of the buyer, a strategy of the buyer, a pure strategy maps her histories and a current price offer to an accept-reject decision. And I'm usually going to use mu to denote beliefs. So here's my solution concept. So I'm going to focus on PBE of this game that satisfied 2 conditions. So let me go through the first. The first condition basically says that this is a separating equilibrium. So at all histories of the seller, this is the set of prices that the seller would post if her costs are high. And this is a set of prices that she would post if her cost is low. So these 2 sets don't intersect. So the seller's price offer perfectly reveals her cost. The second condition says, well, suppose that HTB is a history of the buyer such that at that history, the buyer assigns probability 1 to the seller's cost being low. Then I'm going to require that for all histories of the buyer that follow that history HTB, the buyer keeps assigning probability 1 to the seller's cost being low. This condition is natural in this formulation of the model in which the low cost is absorbing. When I look at the model without an absorbing low cost, I don't have this condition, but for this case, it's a natural condition. So I'm going to use sigma R for revealing, to denote the set of PBE that satisfy these 2 conditions. And I'm going to do, one more. I'm going to, put one more condition that says that on the path of play, at all histories HTS that arise on the path of play, if the seller's cost is high, the seller is going to use a pure action, so she's not going to randomize. I can do, randomization by the seller. It just makes the exposition a little bit less clean. And in the paper, I also do, discuss other equilibria, and if I have time towards the end, I'll do that too. But, for most of the talk, I'm going to focus on this revealing equilibria.
Juan, just a clarification.
Yes.
So in your sort of refinement 2,
yes,
you're requiring that the tau histories include the ones that are off path after an on
yes.
path?
So on the equilibrium path, this would be without loss in this revealing equilibria. So this has bite off the path of play. So in a PVE, depending how you define PV, but if, in a weak PV, you could certainly have that off the path of play, suddenly, the buyer assigns probability 1 to something that, or positive probability to something that before he thought it was not possible. And I'm ruling that out.
Okay, thanks.
But yeah, this is on and off the path of play. Yeah. Okay, so let me describe as a starting point the first best outcome. So rho here, I'm going to define it to be, this is the expected discounted time until cost reaches CL, condition on the cost today being high. And V star is the solution to this equation. So if you're a buyer with valuation V star, the surplus you generate by buying when cost is high is equal to the expected discounted surplus you generate from buying when cost is low. Remember that CL is 0. So the first best outcome is very simple. The buyer is going to buy at time 0 if her valuation is above V star, and she's going to buy when the cost is low, the first period at which the cost is low, if her valuation is below V star. So sometimes I'm going to refer to V star as the efficient cutoff, and I'm going to maintain this assumption that V star is inside the support of the value distribution. So now this, if V star was larger than V upper bar, the high cost would be irrelevant in this model. No one would trade when cost is high. And basically, on the other side, this says that V lower bar is sufficiently low. Okay, so let me describe some preliminaries of equilibrium behavior. So in any PV of this game, not only in my refinement, but in any equilibrium of this game has to satisfy this so-called skimming property that, in words says that buyers that have higher valuation buy earlier. That's just follows from incentive compatibility. Formally, at any time t, there's going to exist some cutoff kappa t plus delta, such that the buyer at time t buys if and only if her value is above kappa t plus delta. Here I'm simplifying. This cutoff might depend on the history. So kappa t plus delta is the seller's belief cutoff. So the seller's beliefs at each period are going to be a truncation of the original distribution. The second condition is holds in my equilibrium set, and since the equilibrium is revealing, and since there was that second condition that once the buyer assigns probability 1 to the seller's cost being low, she's going to keep on assigning probability 1 to the low cost on all future histories, both on and off the path of play. When the cost reaches CL, continuation play in this game is going to coincide with the equilibrium play in the game of one-sided private information in Friedenberg, Levin, Tirol, or Gunst, and Wilson. So having this low cost absorbing basically means that I don't have to characterize what happens on the path of play when cost reaches CL, because these papers characterize that for me. Actually, I have this assumption that V lower bar is larger than CL, which is the so-called gap case. These papers show that there's a unique equilibrium in that gap case, and that equilibrium is weakly stationary. The state variable is the belief cutoff of the seller. So,
Juan?
Yes, go ahead.
Juan, sorry, I have a question. Is there an issue of existence of an equilibrium that satisfies your refinements? Because I just would imagine that if you reach this absorbing cost and you are supposed to reveal it, then why would you do that?
Yeah, this is going to come. There's going to exist, and there's going to exist many of them. I'll show you exactly. can I defer this for a little bit? I'll show you that an equilibrium exists. I'll have a theorem that characterizes and implies existence, but we can come back to that in a minute. But the short answer is that there is going to exist an equilibrium. It's going to be inefficient because of information revelation constraints, but there's going to exist an equilibrium. So kappa, for any belief cut of kappa, PL of kappa is going to be the price that the seller is going to offer this one-sided private information game when her belief cutoff is kappa, and pi L of kappa is going to be the seller's continuation profit in this one-sided private information game. So basically, as I said, all that's left to characterize is really what happens on the path of play when costs are high. So if you fix one of these revealing equilibrium, and I still haven't shown that an equilibrium exists, but let's suppose for now that an equilibrium does exist, then that equilibrium is going to induce sequences of prices and belief cutoffs. And this is basically the way equilibrium is going to play out when the seller's cost is high. So if at time t the seller's cost is high, then she's going to post this price PTH, and the buyer is going to buy if and only if her valuation lies between kappa t plus delta and kappa t. And then if at time t, if t is the first time at which cost is low, the seller is going to post the corresponding price in the one-sided private information game. That's her belief cutoff at time t, if that's the first period at which costs are low, and she's going to earn these continuation profits. And this is an ugly expression, but all that it says is that if you fix a sequence of prices and belief cutoffs that describe the path of play when costs are high, then I can compute what the seller's profits are going to be given those sequences. So at time t, the seller is going to post price PTH. If she makes a sale, she gets PTH minus her cost CH. And this is the conditional probability with which she makes a sale. And if she doesn't make a sale, tomorrow cost might be high. She'll get her continuation value with high cost, or her cost might be low and she's going to get her continuation value when costs are low. All right, so now here I'm going to answer, I'm going to provide my first result provides a characterization of this set of equilibria, and it's going to answer Marcin's question about existence. So suppose that sigma mu is an equilibrium in my class of revealing equilibria. So sigma mu is going to induce a sequence of prices and belief cutoffs. Then belief cutoffs have to be decreasing. And moreover, for all times t, these sequences have to satisfy these three conditions. So let me go by one by one. The first is the standard indifference condition of the marginal buyer. At time t, the marginal buyer is this buyer with valuation kappa t plus deltas. She should be indifferent between buying at that time or waiting until next period and buying next period. And next period, she might face this price PTH, PT plus delta H, or she might face this low price if cost falls. The second constraint is going to follow from the seller's incentive compatibility constraint, and I'll explain this in a second why the constraint takes this form. But basically, what it says is that the probability of trade when costs are high cannot be too large, so it's going to be bounded by this expression. And this is going to be enough. This condition has to hold to guarantee truth telling or incentive compatibility by the seller. And then the third condition says that, well, these are the profits that the seller gets at time t when her costs are high. Those profits cannot be lower than what she would get if she just waited until her cost falls and she played the continuation equilibrium. So the first condition is the standard indifference condition. The last condition requires a little bit of an argument, but it's pretty intuitive. In the next slide, I'll show you where the second condition comes from. But before doing that, let me show you the second part of the theorem and then answer Marcin's question. So the second part says that there exists some cutoff delta upper bar such that if the time between periods is lower than delta upper bar, if you give me any sequence that satisfies these three conditions, I can find a revealing equilibrium that induces those sequence of prices and belief cutoffs. So let me just say a word about existence. When delta is small, there's always sequences of belief cutoffs and prices that satisfies these three conditions. So for instance, you can have a sequence in which the belief cutoff is constant at below upper bar, and the price is constant and satisfying this condition. And it's not too hard to see that that's going to satisfy the three conditions, because the probability of trade is going to be 0. And basically under that equilibrium, the seller's profits are going to be equal to what you would get if you just delayed trade until cost falls. So existence, for at least for small delta, there always exists an equilibrium. In general, the equilibrium is going to be more efficient than just waiting until, delaying all the trade until cost falls. And let me explain in a second. Let me first explain why this second condition has to hold, and then let me say a word about how I prove the second part of the theorem. So this second condition, to see why it holds, suppose we fix a history of the seller such that yesterday her cost was high and today her cost is low. So this was margins question. If she reveals that her cost is low, she's going to get these profits when she reveals that her cost is low. But she could deviate and pretend that her post this high price and pretend that her cost is high. If she does that, she's going to sell with this probability. And if she doesn't make a sale, then she can reveal that her cost is low tomorrow. So this incentive constraint just says that that deviation is not profitable, and this must hold in any equilibrium. And coming back to Margin's question, the reason why in equilibrium the seller doesn't want to do that is because if she reveals that her cost, if she continues pretending that her cost is high, she's making sales with such a small probability that it's not worth it for her. So for the second part of the theorem, suppose that this sequence is satisfy the three conditions, then I can construct a PV that satisfies the following. So on the path of play, when costs are high, the seller is going to charge the corresponding price in the sequence, and the buyer is going to accept as long as her value is between kappa t plus delta and kappa t. When costs are low, play is going to revert to the one-sided private information equilibrium. So note that because of that indifference condition of the buyer, fixing the strategy of the seller, the buyer, is behaving optimally here. And she's also behaving optimally when costs are low because they're playing the continuation equilibrium of the one-sided private information game. So the only incentives that need to be given really is to the seller that has a high cost. She should have an incentive to post this price. Well, I can construct an equilibrium under which if the seller ever deviates from her corresponding price, then the buyer is going to assign probability 1 to the seller's cost being low. And so, she's going to accept only low prices. And if delta is very low, those prices that she's going to accept are going to be very close to the lowest valuation, so by the cost conjecture. So this is going to be enough to deter the seller from ever deviating from that sequence of prices. And moreover, one result in Friedenberg, Levin, Tirol, and Gould, and Wilson was that Equilibria, in the gap case, is always weakly stationary. Here, this equilibrium that I construct to support those sequences can be taken to be weakly stationary as well. So weakly stationarity is without loss in this class of equilibria. Okay, so this second result speaks about the inefficiencies that arise in this class of equilibria. So as I mentioned, equilibrium is going to be, there's going to be inefficient delay because of that incentive revelation constraint or information revelation constraint. But you could imagine that there's a different type of inefficiency that might arise, that it's that a buyer that has a low enough valuation might buy when the cost is high, or she should wait and buy when costs are low. What this proposition says that is that second type of inefficiency never arises in this model. Buyers that have a valuation lower than B star never buy when cost is high. So I'm going to skip the proof for the sake of time, but basically the proof just shows that if you were to sell to a buyer that has valuation lower than B star, then you would be violating this third condition. The seller would be better off just waiting until costs are low rather than sell to her when costs are high. Costs are too high to serve that type of buyer. Right. So for my second set of results, I'm going to look at there are many revealing equilibria. I'm going to look at the most efficient one of those. And under the most efficient revealing equilibrium, the incentive constraint of the seller is going to hold with equality while her belief is above the efficient cutoff. If it didn't hold with equality, we could sell a little bit more with a bit of a higher probability, and that would be more efficient. So the seller's constraint is going to hold with equality. So for each delta, I'm going to now parameterize these sequences by delta. So these sequences are going to be the way the path of play looks like under the most efficient revealing equilibrium when the time between offers is delta. And then B star was the efficient cutoff. That efficient cutoff depends on the time between offers. As the time between offers goes to 0, you can show that it converges to this value. So I'm going to define B hat to be that limiting value of B star. All right, so now I'm ready for my second result that says, basically it characterizes that limit of efficient equilibrium. So there are two functions, pH and kappa h. pH maps time to prices, and kappa h maps time to points in the support of the distribution of values, such that at time t, the price that the seller is going to charge when her cost is high in the limit as delta goes to 0 is going to converge to this function pht, and the seller's belief cutoff is also going to converge to this cutoff kappa ht. So these functions basically describe the path of play while the seller's costs are high. We know that when the seller's cost is low, we're going to have the cost conjecture, so the seller is going to post price below or bar immediately, and the game is going to end. These functions satisfy a system of differential equations, and I'll explain in a second. These differential equations have clean intuition. I'll come back to those in the next slide. There are two boundary conditions that have to hold. The first is that at the start of the game, the seller's belief cutoff is the highest valuation. So at the start of the game, every valuation is possible. And then, under the most efficient equilibrium, the seller is going to keep selling to the buyer as long as her belief cutoff remains above the efficient cutoff, which in the limit is P hat. So T hat is going to be the point at which the belief cutoff reaches B hat. And at that point, the seller is going to charge a price that leaves this marginal consumer indifferent between buying at that price or waiting until cost falls, which that's the expected discounted value of waiting, and then getting the good at price below or bar. And after you sell to this guy that has valuation B hat, you're not going to make any more sales. You're going to wait until cost falls and sell at that time to all the other consumers. So, and let me explain in words or give an intuition as to why these two equations make sense. So the first equation basically follows from the buyer's indifference condition. So this guy kappa ht is the marginal buyer at time t. This is the surplus that she gets if she buys at time t when costs are high. So that's the cost of delaying her trade for an instant. If she delays her trade for an instant, prices, if cost remains high, are going to fall at this rate, and with this instantaneous probability, the seller's cost is going to fall, so the price is going to jump from pH to below or bar. So basically, the left-hand side is the benefit from delaying trade for an instant. The right-hand side is the cost of delaying trade for an instant. So that just follows from the marginal buyer's indifference condition. And then the other equation follows from the seller's IC constraint that holds with equality. So if you're a seller whose cost just turned low, on the path of play, you should charge in the limit below or bar and sell with probability 1. So the cost of delaying that, of getting that below or bar an instant later, is R times below or bar. If you can, instead of revealing that your cost is low, you can continue pricing high at PHT. If you do that and you make a sell, you're going to sell at PHT rather than below or bar. And this first term is the probability with which you make a sale in that instant, because that's the speed at which the belief cutoff is falling, and that's the conditional probability that the buyer's valuation is at the belief cutoff. So this follows from the seller's IC constraint binding. Okay, so I'm gonna skip this. I have some comparative statistics about how the prices that the seller charges and the rate at which he sells change with changes in the distribution of values, with changes in the high cost of the seller, and with changes in the speed at which cost falls. So for instance, let me just say one. So for instance, if the value distribution F increases in terms of the reverse hazard rate, this is the price at which a buyer with valuation kappa buys when costs are high. That price is going to increase, and the rate at which the seller makes sales is going to fall. And similar comparative statistics hold for the other parameters of the model, but in the interest of time, let me not go over them. I want to go to this, and this probably it's related to the intuition that Martin had at the beginning, that what's driving information revelation here by the seller? Why would the seller reveal that her cost is low? Well, you can do the classic limit of taking the lowest valuation down to the lowest cost, which in this case is 0. And what happens here is, as V lower bar goes to 0, basically the rate at which the seller makes sales when costs are high is going to go to 0. And that follows from this term here. If V lower bar goes to 0, you can show that this price is always going to be bounded away from V lower bar. So the rate at which the seller makes sales has to go to 0. That just follows from information revelation. Then the seller's profits go to 0. So you can relate this to what happens in the usual cost conjecture world. As in Freudenberg-Levin Tirol or Gunn, Sonnenschein, and Wilson, the seller's profits are going to go to 0 when, in the gapless limit. But in contrast to those papers here, inefficiencies are going to be much larger because there's almost going to be no trade while the seller's cost is high. Right. So for my last result, I'm going to look at this model in which, so it's the same model as before, but now I'm assuming that these costs are publicly observed. So buyers can observe the seller's cost. And I just want to contrast, just to provide an intuition or to sort of show that it's the private information that is driving these inefficiencies. I want to contrast the result that I just showed you to the world in which these costs are publicly observable. And that's related to a model that I studied in a previous paper that came out in TE. I mean, there are some technical differences, but I don't want to go over them. And I'll show you basically the results that relate to this model. So it's the same model as before, but now the cost is observed by everyone, it's public.
Do you still assume that the low cost is an absorbing state?
Yeah, actually, the result that I'm going to show you now holds also if the low cost is not absorbing, but for ease of exposition, I'll continue to assume absorbing state cost. The two results actually, the results that I presented before also hold when the lowest cost is not absorbing, but the argument, you need to work much more because now you cannot, kind of hook onto previous papers to see what the continuation play is going to be when costs are low. But if I have time towards the end, I'll show you what, how I generalize the results to that case. Actually, in this paper, I don't assume that the low cost is absorbing. But
Juan, sorry for interrupting. You have 10 minutes left.
Okay, thanks. Yeah, that's enough. So for each time period delta, let sigma delta and mu of delta be a weakly stationary equilibrium of the game with public cost. You can show that a weakly stationary equilibrium always exists in this game. And let pi pub of delta be the seller's profits at the start of the game under the corresponding equilibrium, conditional on her initial cost being high. So because the low cost is absorbing, and now the cost is actually publicly observed, when costs are low, continuation play is going to coincide with equilibrium play in Freudenberg, Levin, Tirol, and Gunn, Sonnenschein, and Wilson. So again, when costs are low, we're going to get this Gaussian outcome. So again, I need to characterize what happens when costs are high. And what this result shows is what happens in the limit of weekly stationary equilibria as the time period goes to 0. So along this sequence in the limit, the equilibrium outcome is going to be efficient. Buyers that have a valuation above the efficient cutoff are going to buy at time 0. Buyers that have a valuation lower than the efficient cutoff are going to buy the first time cost reaches CL. Let me jump to the second point and go to the third. The seller's profits when her costs are 0, when her initial costs, are CH, converges to this value here. So this value here is, if you think of a different market in which the buyer's valuation was below or bar with probability 1, in that alternative market, the seller would get these profits because her optimal strategy would be to wait until cost falls and then charge a price equal to below or bar. So this is what the seller would earn in that alternative market. What this is showing is that even if the buyer's valuation is distributed in an interval, the seller's profits are exactly what she would have gotten if the buyer had the lowest valuation with probability 1. So basically, this is another way of saying that the seller is unable to extract rents from buyers with higher valuation. And this is exactly what happens in the classic cost conjecture. And then for the second result, basically when costs are high, the seller's initial price is going to converge to this object here. And basically what's going on here is that you're getting efficiency and you're getting no rent extraction, just as in the standard cost conjecture. But in contrast to the standard cost conjecture, different types of buyers are buying at different times because that's what efficiency implies. So some buyers buy earlier, some buyers buy later. Those buyers that buy earlier have to buy at a higher price. And this is the price at which those high value buyers buy. The thing is that the seller, she's selling to them at a higher price, but she has a higher cost also. So her profit margin from selling to those buyers with high valuation is exactly equal to the expected discounted profit margin that she gets from selling to someone with valuation below or bar. So, this is how, points 1 and 3 can live together. So, this equilibrium with public cost retains, the key Gaussian elements. The equilibrium outcome is efficient in the limit and the seller cannot extract rents. And, it's the buyers with higher valuations that are better off because, they are able to sell at a lower price, to buy at a lower price and earlier. Buyers with low valuation, they are indifferent. So all these extra benefits go to the high value buyers. So how much more time do I have? Sorry.
Oh, Ting, you're muted. But Juan, basically,
I think 7 minutes.
7
right,
minutes.
but we want to leave some time for questions, or at least pause to see if people have questions. Otherwise, you're welcome to use all of the time.
I'll use 2 more minutes and then end. So there are some extensions, the game admits many other equilibria, but let me not talk too much about that. As I said before, I can generalize to the case in which the low cost is not absorbing, but in the interest of time, let me not talk too much about that. What happens is basically is that even if the low cost is not absorbing, at least if you look at weekly stationary equilibrium, the seller's profits are still going to converge to below or bar when costs are low. So the classic Gaussian forces are going to kick in still. And this allows me to generalize all the results that I had before. Let me spend some time, 2 minutes talking about this last result that I have. So, this is certainly not the first model that features inefficient delays. And far from it, there are many, many bargaining models that have that. But let me just say that, if you, at least most of the papers that I can think of, maybe not all of them, but, at least in these models with private information, those models that feature delay, the environment that those models study are such that, the environment doesn't admit a feasible mechanism, so a mechanism satisfying ICIR and budget balance that achieves efficiency. So for instance, Cho and many others study models with two-sided private information, but in those models, the equilibria are inefficient if and only if the support of buyer's valuation and seller's cost overlap. And we know from Myerson-Satterthwaite that in that case, there's no feasible mechanism achieving efficiency. there are models with correlated values that have inefficient delay, and for instance, Denneker and Liang and Fuchs and Skripach. But in these models, and this is actually a result in Denneker and Liang, that as long as values are positively correlated, the equilibrium is going to be inefficient if and only if there's no feasible mechanisms that is achieving efficiency. And Fuchs and Skripach, although they think about arrival of public information, that really generates correlation across valuation. So it's really within the Denneker and Liang world. So in these models, we know from the start that equilibrium outcomes are going to be inefficient. And what these papers do is characterize how those inefficiencies play out in equilibrium. But we know from the start that efficiency is not attainable. And I'll end with this because I don't have enough time to show you the mechanism, but that's not necessarily true in the model that I study. At least under some conditions, there exist mechanisms that are feasible, that are ICIR and budget balanced, that implement the first best. On top of that, I have a result in the paper that says that any equilibrium of the game, revealing or non-revealing or pooling or semi-separating, any equilibria, even if you look at limits of equilibria as the time period goes to 0, you're always going to get inefficiencies. So in this world, inefficiencies are efficiency is feasible. There are mechanisms that attain efficiency. It's just that in equilibrium, we're never going to attain that. And if I had a little bit more time, I would tell you about the mechanism that implements efficient outcomes, but I'll stop here for questions to give time for the transition.
Any questions from the audience? Actually, I have a question for Juan.
Yes.
I'm wondering, so you mentioned that because PPE, you have a large set of equilibrium.
Yes.
Can you comment on the seller's profit in this revealing equilibrium with other equilibrium, say pooling or semi-pooling? Do you have any thoughts on that?
So there's certainly so there are many other equilibria, and these equilibria are not in general are not the most profitable for the seller, for sure. I mean, they're actually, in this game there are pooling equilibria. So if you think about pooling equilibria, the benefit of having a pooling equilibrium is that in a pooling equilibrium, that information revelation constraint that I had that drives all the inefficiencies doesn't need to be satisfied. So there are pooling equilibria that are more efficient than this separating equilibria that I described. And I mean, I'm pretty sure, although I haven't calculated them, that they're pooling equilibria under which the seller would make more profits than this separating equilibria.
Okay.
So, I mean, that's a good point, and I take it. This is one class of equilibria. I think it's natural, and it's kind of a natural point of comparison to previous equilibria in the literature. But the point is well taken.
Thank you. Any other question? Okay. Thank you, Carl. Thank you for a great talk.
Yeah,
and
thank you.
There's